So next up we have Dr. Schiozer, Dennis.
It's missing one slide there, but that's okay. Good morning, good afternoon. It's a pleasure to be here. Thank you, Energy Simulation, for organizing this event. Thank you for attending. The idea here is to present part of our work and that we do at the University of Campinas in Brazil, in a lab called Unisim. We are dedicated for reservoir simulation and management. And it's very important for us to show that we have to integrate with geoscience, with production engineering, economic evaluation, and data science in order to do good forecast and good decisions. Our team is about 80 people concerning researchers, students, administrative professors, and IT people. And today I'm going to present part of the work we are doing there, which is called model-based reservoir management in 3 stages. We are trying to divide the decision analysis in 3 steps and 3 stages: a life cycle, short-term, and real-time. So this challenge started like 3 years ago when the companies in Brazil asked us to, can we use these simulation models for short-term decisions and real-time decisions, because they want to apply the decisions in the digital fields. And also the other challenge was that the pre-salt reservoirs, thank you, Leonardo, for the presentation about how is the situation in the pre-salt in Brazil. We have giant fields with a lot of oil there to produce, but very complex carbonate reservoirs that take a long time to simulate. And if we want to take good decisions, we need to do a lot of simulations to do it. So it's a very time-consuming, so we are trying to do good decisions in less time. So the objective here is to develop methodologies to improve this quality of short-term production forecasts and decisions. In order to do that, we are also trying to integrate with machine learning and apply to real-time decisions and digital fields. So at the end, we want to contribute for efficient energy production. I've been presenting this scheme for a few years right now. I'm going to change a little bit the focus of the presentation only. Here's is what we do. We have the reservoir. We divide this scheme in colors. The green color is dedicated to build the models. So first, we try to collect all the data we have, including uncertainties, to build this, what we call high-fidelity models. But the high-fidelity models are very time-consuming to do it, so we try to do simplifications to what we call fit-for-purpose models. And we are now using multi-fidelity models because depending on the objectives, we change the characteristic of the model. Once we have these models, we go into this blue part with the life cycle decisions, which normally the reservoir engineers are concentrating these blue decisions there, which are the decisions until the end of the reservoir's life. Once we have this decision and we implement in the reservoir, we collect dynamic data like seismic 4D, well data, and so on, and we go into the red part here, which is the history matching or data simulation part, in order to reduce uncertainties and improve the quality of the models. But today I'm going to concentrate in the black part here and blue and black part here, which is the short-term decisions. And I simplified the other parts here to show the 3 stages. So it's the same thing as the models. We have high-fidelity models, then we simplify the models to take decisions. The idea here is the same. We have the life cycle decisions, which are very complex. When we try to take these decisions as set points for short-term, which you put here in gray for short-term decisions. And what we call short-term here is the size of the cycle of the closed loop. And once we have the decision for this short-term, we go to real-time. So that's the whole idea. In order to do that, we are following our 12 steps that I have been presenting in the previous years here as well. We have the green steps to build the models. We have the red steps to reduce uncertainties and improve the quality of the models. Then the blue part, which is very complex, we divide it in several stages. We need first to set the production strategy for the base case. We perform a risk analysis. Then we select some representative model, which are representative of the scenarios we have, the uncertainties. Then we find the best decisions for each scenario in step 9. And in step 10, we find the robust decision, which would be the best decision concerning all the uncertainties that we have. And in step 11, we integrate with production facilities and we take the life cycle decisions. We are doing that for a few years right now, but this takes a lot of time. I'm going to show today. We are trying to simplify this process and intensify the decisions in the step 12, which is the short one, the short-term one. So we divide also our variables in 3 groups. The group 1 are the variables of the design variables, for example, the platform capacities, the well number, the well positions, and so on. The group 2 are how we control the wells and the system. And group 2 is the revitalization fields. For the pre-salt, for example, they are very important because we have second waves and other waves because we have limited production for the gas production in the platforms. So these revitalization variables are important in how we change the wells in the future. And the colors are the same here. We have the modules in green. Then we take the life cycle decisions in blue, group 1, group 2, and group 3. When we finish that, we have the set points for the short-term decisions, which are taken in gray and black. And the whole idea here is that instead of taking very complex decisions for all the variables until the end of the reservoir's life, we concentrate in the variables that we are going to apply in the next loop. So that's what we do in gray. So first we do this blue part here. So instead of taking 5-6 months to do a very complex process and decisions, we do a very fast procedure. We take the best decision that we can in the time we have, then we go to short term. We try to manage the field in the short term, and in parallel, we keep running the other picture like I'm gonna show here. So first the blue, then the gray, and the idea here is to divide this in three stages. We're gonna present this in an SP conference in the beginning of 2024. And first, the life cycle decisions. We have to include all the uncertainties, perform risk analysis, probabilistic decision, and so on. For the pre-salts, we need hours to run each model, so it takes months to take all the decisions we can. So what we are trying to do is to get approximate solutions with lower fidelity models and lower fidelity processes, and use this as set points for the closed loop decisions. The second stage is the closed loop decisions. We concentrate only in the variables that we are going to apply in the next weeks or months, for example. Then we take the decisions, and we have shown also that to do that, we don't have to use very probabilistic analysis because the models don't change too much in the near future. So we can do deterministic analysis. Once we finish the decisions, we check the effects on the life cycle, and then we go to the third stage, which is real-time optimization and implementation, similar to a digital twin. And this real-time is important because we have a lot of operational problems that can occur in the short term. In parallel, we can run the life cycle decisions in background. If something changes, we can go back and start the process again. So this is the scheme. I hope it's possible to understand there. We have the stage 1, group 1, group 2, and group 3 variables, set points for the group 2, stage 2. Then we take the decisions for the short term. In parallel here, we can run the stage 1 in background. So while we are implementing the decisions, we can keep running the process in life cycle. If some decision changed, I can start again the next cycle and so on. And if we have any operational problem, any failure in wells, for example, any problems in reinject the CO2 into the reservoir and so on, I can go into the real-time decisions. So the advantage of doing that is that life cycle decisions are very time-consuming, so we can simplify the process. We can do it very fast, closed-loop cycle optimization. Then we can implement them very fast in the reservoir. We can run the life cycle optimization in parallel. If something happens, we can change the decisions. And if we have operational problems, we can go and change the decisions instantaneously into the reservoir. We are trying to develop a concept similar to a digital twin here. In order to do that, 3 years ago, it looks easy, but we had a lot of problems to implement these things. The first thing that we realized that the current models that we use are not good for short term. They are good for life cycle, but not good for short term. So we had to improve the quality of the models, especially for the short-term forecast. Then we had a lot of problems to understand how the boundary conditions, which comes from the integration of the production facilities, will affect the problems. So we first had to integrate with the production systems. Then we had to develop the concept of the human intervention free, which is the boundary conditions. Of course, if someone goes there and close a valve, things will change, so we have to react to that. We implemented the conditions of a prescribed operation. There was a suggestion from the last year's summits. And the prescribed operations are everything that we can set up from the beginning. For example, the size of the cycles for the injection, everything that we know that's going to happen in the future. In steps 3, 4, and 5 here, we are trying to integrate with machine learning. We didn't get good results in the beginning, so we are trying to now use some physics-based machine learning, filtering the machine learning forecasts based on the restrictions we have from the system, and also using hybrid approaches, data-driven helping the models, and probabilistic model-based helping data-driven to get good results. We finished the 2-stage optimization. We're going to present the works in this SPE conference. And now we are getting the first results of the 3rd stage, which is the real-time digital twin implementation. So in this methodology, first I'm going to show an example. Here's a probabilistic analysis of a benchmark that we have there from the pre-salts. As we go from the history to the forecasts, we can see that all the models are history matched in the past, but when you change to filter conditions, the productivity and injectivity of the wells have to be very well calibrated, and it's not very easy to do it probabilistic because we have several models to do it. But the effect of that on life cycle is not so important, but the effect of that in the short term is very important. As you can see here, we can have 50% errors in the rates and so on. So we had to calibrate very well the productivity and injectivity of the wells. In the bottom, we can see that as we do that, we go from this indicator that we call NQDS, which is the quality of the history match. In the green parts, for the life cycle was okay. Between 5 and -5 was okay because the behavior was okay. But for the short term, the errors were very big. So we have to develop a way to calibrate this productivity for each of the models that we are going to use for the forecast. And then we have the blue results there, which is much closer to 0. So that means that the models are much better for short-term forecast. We also had problems to integrate with production facilities because we have models also that try to model the surface facilities, and they are also wrong. So we have to calibrate these models. We have to use past data to calibrate and how the pressure drop in the well and so on. And here I'm showing an example and how we can improve the quality of that. And this is also very important for us to get short-term forecasts, good for short-term forecasts and decisions. And finally, I'm going to present here the 3 stages optimization based on this benchmark model that's called Unisyn 2026, which is a pre-salt reservoir. The complete procedure to optimize this using the 12 steps would take us about 6 months to run because we have a lot of models, 9 representative models. Every time we do a robust optimization, we have to run 100 iterations and 30 years of simulation time and so on. So we simplify a lot the process using just 3 representative models. Instead of running 30 years, we are running 20 or 22 years just to have an idea how the strategy was. We didn't need to run the full simulation time. We reduced the number of samples to optimize and so on. So other simplifications, instead of running 6 months, we could run in a week, for example, the optimization. And we are using this as a base or a set points for the operation for the next months. So we perform the entire 12 steps, build the models, then we data simulation process, 47 filtered models, then basic strategy for the P50, initial risk curve, the selection of representative scenarios, and then perform the optimization. Once we finish this optimization, we are implementing the 3-stage optimization process. Here's just an example from stage 1. We optimize getting these red results, and for the optimization of the stage 2, we can get better results for each of the representative models that represent uncertainties in this process. Of course, the percentages here are not very high because we have to improve this every cycle. Every cycle we have a 1%, 2% improvement because we increase a little bit the quality of the decisions in every time we do this integration. And we can see here in average how they behave. In the top left, we have the short-term, the representative models response to the short, first for the base case, then for stage 1 and stage 2. We can see that we can improve the results. In the right top, we have the short-term behavior for the full ensemble, that we can see the results are better. In the bottom left, we have the effects of these decisions in life cycle for the representative models, and in the right for the full ensemble. We can see that doing that, we can improve the quality of the results. All the models have better response, as you can see in the risk curve here. So this is just one loop of the closed loop. When we finish that, we are ready for implementation in real time. Once we finish that, we go to real time, which is we have to react to all these problems that occurs in the real life. Wells having problems, and sometimes we don't have enough wells to reinject all the gas and so on. So we have to do this optimization in short term. Here's just an example, but we have published other examples as well. So first we have to decide if the well is operating in full potential or restricted. Then we have to implement the prescribed operations, for example, the cycles, how much gas and water we're going to inject, what are the conditions for the producers and injectors, and so on. And every time we have a problem, operational problem, we go there and correct, improving the quality of the results. An example of that is sometimes for the life cycle, we think the models can reinject all the CO2 back to the reservoir, but in real life, when we get there, we don't have wells enough to put this in the reservoir, so we have to change the conditions and change the operations in short term. So in a way, we divide this process in these 3 stages, and that allows us to operate the wells much better than we used to thinking in a life cycle. And what we are implementing right now is like a digital twin model where we have the relationship between producers, between producer and injectors. And once we have a problem, for example, in one well, as we show here in the example in P11, we know what to do with the other wells and with the injectors immediately. With this, we can optimize immediately in the optimization of the operation of the field. So as a summary, we completed this optimization process that would take us 6 months. Would take us 6 months to do it. We did in a few weeks. And then in parallel, we keep running the optimization for the full field. But we have already an operation that we can optimize in the closed loop. In our case, the closed loop is 6 months. So we have the operation for the next 6 months. And then this is the implementation. We idealize for the field, but if you have problems, we go there and correct in the short term. So we can do the 3 processes in parallel, and we hope this will improve the quality of the solutions for the management of the pre-salt fields. So what's finishing all this, we are trying to improve the quality of the management for the pre-salt fields. There are giant fields with permanent 4G, intelligent completions, WAG cycles, WAG CO2 injection, and so on. So it's a very complex problem. So instead of taking 6-7 months to do a decision, we can do it in a few days. We are applying, we improved as well the green part there, because instead of running one model only, we have a multi-fidelity model. Each model has a different fidelity for each type of decision that we are taking. We have improved the history matching data simulation part, especially for the short term, and especially for the integration with the production facilities. Normally, the reservoir engineers don't do it very much, but the boundary conditions for the reservoir are very important for us to predict how much we're going to produce in the next days. And we have divided this decision process in 3 stages, trying to do the same thing that we do for models. For models, we first have a high fidelity models, then we simplify the models to simulate them on time. The decisions are the same. First, we have these life cycle decisions that are complex, but they can simply be simplified to short-term analysis. That's the same idea. And this is the final step that we are taking to build a digital twin and digital field management for the reservoir. So with that, I would like to acknowledge the work of the researchers, students, professors, and team there, and the sponsors. Thank you very much for your attention. I'll be glad to answer questions.
Thank you, Dr. Schiozer. Any questions? So,
Sure.
Benham Jaffa from USC. Thank you for the presentation. This is actually a very nice introduction to my talk in the afternoon. So, you mentioned somewhere in your talk that for low fidelity models, you tried machine learning and it didn't work. Can you elaborate on that?
Yes.
What happened?
Yeah, it's a problem that we are having there, especially for the prescribed operations. For example, in the future, there are operations that we know they are going to happen, but they didn't happen in the past, but they will happen in the future, so machine learning cannot get that very well. So we have to do a machine learning forecast, but we have to include this type of operations in the future. For a life cycle, this is not so important because in average, the machine learning can get the results. But for short term, when, for example, an injector will change the cycle. It was injecting water, then it's going to inject gas. If we don't inform machine learning that operation will happen, machine learning will never get it. If we change the size of the cycle, for example. So we are trying to input this prescribed operation into the machine learning algorithms for them to understand that there are operations that we are doing intentionally and will affect the results. If you don't do it, machine learning will never get it, right? So that's the difficulty we had for short term. For life cycle, it was working okay because in average, the behavior was predictable because we don't really want to know what happens in a few days or so on. But for short term, this was a catastrophe. It was changed a little bit, changed a lot the operations and things. But that's what I mean. Not that the machine learning is not good. It's good, but we have to inform the machine learning that some things will happen in the future.
Yeah, I had a guess that what is probably happening you're trying to extrapolate, right? So during training, you provided information where during forecasts, you're doing something else. You're asking for, and that's usually the case when these techniques fail.
Exactly.
Thank you.
Yeah, because I have a partnership with computer guys there to do machine learning, and they are not expertise in petroleum. I informed exactly that. You're trying to extrapolate something that didn't happen in the past, in the future, and they couldn't get it. So now we are working together for them to understand this behavior to do it. Yeah.
Dennis, thank you very much for this interesting presentation. So from oil and gas, we are very much doing energy transition applications, and the type of and character of the data would be different. We don't have production or injection to just match. It's more about injection production is in our hand to inject or produce if you want to store something, for example. But we get different type of data. We get seismic, for example. We get mechanics, deformation, subsidence, uplift, etc. They come with multi-resolution nature. They come with different type. We want to understand flow, but we get mechanics sometimes data. Would this be different characteristically than doing, let's say, the classical oil and gas history matching data fitting? In what way we should adopt our data assimilation strategy to take care of these kind of new applications?
Okay. Yeah. I think the general procedure could be exactly the same, but of course you have to adapt for the physics that we have to do. The important thing is to have a high fidelity models that can really model the physics of the problem. But normally we want to do that. The time consumption is very high. If you have time to wait, that's okay. But if you don't, you have to react fast. You have to simplify the models. So I believe we can apply the same type of methodology, the 12-step methodology, in order to build the models, simplify the models, make sure the models are validated for the high-fidelity models, then take the decision you want to take.
But then we don't have high-fidelity data. That's the challenge we have.
Then
we
we
have low
include
resolution data
uncertainties.
set. That's exactly it.
Yeah.
So the mismatch between reservoir simulation scale or resolution, better to say, and the resolution of the data that is provided to you is actually, they are not matching.
Yeah,
And then
that's a challenge. Yeah.
That's-
But then we include uncertainties. We can include what happens in the different scenarios if you don't have the data, what's going to happen.
But then the proxy model you present would be good, because then you could upscale the reservoir model, for example, and see how you are
Right,
within that range. Oh, thanks a lot.
Yeah,
Thank you.
you're welcome.
Okay, online question here from Husham Albalola. Do you believe the 12-step CRDM and the 3-stage optimization can be used to all types of models, reservoirs, and development strategies, or do they still need to undergo development and modification in order to improve results and shorten the amount of time it takes to run the models?
Yeah, I believe this methodology is a general methodology. It may be a different name or a different number of steps, but the general methodology that even the industry applied, because you have to build the models, you have to make sure the models honors the past data, and then use these models to forecasting decisions. So I believe that we can use it for every problem, but of course we have to adapt for each type of problem that you have. Not only adapt to the data you have, but adapt for the time you have to take these decisions. And one of the problems that we had for the pre-salt application was taking too much time to decide, because each simulation run was 3 hours. Then we had to perform 100 simulations every iterations, and a lot of uncertainties to include. If you want to do it perfectly, we will never finish. So that's why we are simplifying this process to. Of course, we can keep running in parallel in background. If something happens, we can adapt the solutions, but that's what we are trying to do, simplify the process to take the decisions on time, and then if we have time in parallel, we can run the other process, and if something happens, we can change the decisions.
Okay. Masood Riazi appreciated the algorithm and the approach for optimization. His question is, how many simulation results did you add as data set for machine learning stage?
How many simulation?
How many simulation results did you add as data set for the machine learning? So basically, how many simulation runs you've got for machine learning? Like, do you have to create?
I'm not sure.
Okay.
I didn't understand very well the question. Maybe you can send me an email.
Yeah,
I can try to answer
sure.
later on. But we are, for machine learning, we are using past data. We are not using simulation, right? We use the data
Actual
and
data.
try to forecast based on the past. We are also trying to build the hybrid models that the machine learning are based not only on the past data, but also on the probabilistic analysis of the models. So that's one of the ways we are trying to restrict the machine learning response. But I don't know if that was the question, but I can answer it.
We'll address it later on.
Okay.
Another question, DN. What is the time of the optimization cycle from gathering of the data, running the simulation, adjusting the production/injection in the wells, and obtaining new data? What's the time of the optimization cycle?
Yeah, it was about the time that takes us to do it, 6 months, about 6 months. And the time of the loop you are doing is about 6 months. That's why we had to simplify it, because we are taking the decisions after the decisions have to be taken. So it is about 6 months. The size of the cycle is until the models are valid. So if you have, for example, 10 representative models of the scenarios, if the models are still valid, we keep using the same models for the future. Once we have an indicators that show that the models are not valid anymore, then we perform the data simulation again and new models again. So this is typically from 6 months to 1 year.
Okay, good. All right, so yeah, Josh, you're close before lunch, and so we'll just move on to lunch. Thank you very much,
Thank you.
Dennis.